So good day, Sir Orven. So today I'll be going to present my papers on the multiple linear regression between age in years and weight in pounds and systolic blood pressure. So we start by defining what is multiple linear regression. So it is a statistical technique that uses several explanatory variables to predict the outcome of a response variable. The goal of multiple linear regression is to model the linear relationship between the explanatory, which is the independent variables, and the response, which is the dependent variables. So MLR is used extensively in econometrics and financial inference. Moving on to the background of the study. So systolic blood pressure, the top number measures the force the heart exerts on the wall of the arteries each time it beats. This chart will help us determine if our blood pressure is at a good numbers or an action must be done to improve it. The intent of this study is to determine the multiple linear regression between age in years and weight in pounds and the systolic blood pressure. So this study uses a systolic blood pressure dataset, which will undergo MLR or the multiple linear regression to, to estimate the relationship between the two independent variables. So we have the age in years and weight in pounds. And our independent variable is the systolic blood pressure. So the methods that being used in this study is first is the multiple linear regressions formula. So we have here y is equals to b sub 0 plus b sub 1 times x sub 1 plus b sub n times x sub n. So we have here as the y as the predicted value of the dependent variable, the b sub 0 as the y-intercept. So this is the value of y when all other parameters are set to 0. Next, we have the b sub 1 times x sub 1. So it is the regression coefficient of the last independent variable. Next, we have is the b sub n times x sub n. So the regression coefficient of b sub 1 of the first independent variable and x sub 1. So this is the effect that increasing the value of the independent variable has on the predicted y value. So next here we have the regression of we have the regression analysis. So linear regression is an analysis that assesses whether one or more predictor variables explain the dependent variable. So the R squared is a goodness of fit measure for the linear regression models. This statistic indicates the percentage of the variance in the dependent variable that the independent variables explain collectively. So we have here the formula, which is R squared is equals to 1 minus the unexplained variation divided by the total variation. So after that, we will go with the assumptions of multiple linear regression. So we have the linearity, the normality of the error terms, the no multicollinearity among predictors, no autocorrelation of the error terms, and last is the homozydasticity. So the results and discussion on this paper. So we coded with Jupyter Notebook and Python. So we have here the results. So first here we have is the linear regression. So although we have an R squared value of 96 here, 96%, which shows how well the data fit the regression model, it is not always the case that a high R squared is good for the regression model. The quality of the statistical measure depends on many factors, such as the nature of the variables employed in the model and the units of measure of the variables. Also, the applied data transformation. So we have the first assumption result. So we have here the linearity assumption. So as we can see in the graph, so the scatter plot being aligned on the diagonal line. So it shows that the linear relationship between the outcome variables and the independent variables. Next, here we have the assumption number two, the normality of the error of terms. So the model shows that the residuals are normally and equally distributed. Using the Anderson-Darling test for normal distribution, we got a p-value of 0.42, which concludes the presence of a normal distribution. We have here the assumption number three, the no multicollinearity among predictors. So using the variance inflation factor, the VIF values, we got a certain multicollinearity among variables. So this shows that predictor used in the regressions are correlated with each other, and the coefficient interpretability will be problematic. Going to assumption number four, so the no autocorrelation of the error terms predictor. So by performing the Durbin-Watson test, we got a 1.8 value, which resulted in little to no correlation. And the last assumption, the assumption number five, we have here the homoscedasticity assumption. So the result in this assumption shows that the amount of error in this residual is similar to each point of the linear model. Thus, the scatter plot of residual shows that the data is homoscedasticity. So to conclude the results, with all the statistical data we got by performing the multiple line regression assumption, the independent variables are correlated to each other, and homoscedasticity residuals does not have relative constant variance. So we can conclude that a linear regression model on the systolic blood pressure dataset violates a number of assumptions which cause significant problems with the interpretation of the model itself. Making decision based on a model that has violated assumptions is risky. Although in real-world data, it is not unusual for assumptions to be contravened. So, with all the study on this specific data set, the only recommendation I can recommend to the future researcher is using a large data set, since the data set being used on this specific study is very small. So, it can really affect the whole result with this study. So, I guess that's it. So, thank you so much.